Hey students, there's a warm-up to start lesson 5.5 on complex numbers and roots, and so please take a moment to pause the video and complete the warm-up. All right, let's take a few moments to check over our answers to the warm-up. How did you do? Well, let's take a look at what we have in store for us in this lesson today by looking at the learning goals. Our first learning goal of the lesson 5.51 is to simplify square roots of negative numbers. Wow, negative numbers. Up to now, we've pretty much stayed away from all negatives when we deal with radicals, with taking square roots, that is. So today we're going to learn how to deal with square roots of negative numbers, which we've always been told are taboo, that you just can't do. But our calculator can't do it, but we can. And secondly, we're going to learn to solve quadratic equations with complex roots. And then third, we're going to find complex zeros of quadratic functions. So we're going to learn what it means to be a complex number, and we'll learn how to actually find complex solutions or zeros of quadratic functions. Okay, so let's say we were given this function f of x is equal to x squared plus 1. If we were to be asked to find the zeros using a graph, we'd actually have to take a look at what this function looks like. So one way we could do this is by just typing that in our calculator and looking at the graph. But I'm going to go ahead and sketch this in the margin here, and then we'll take a look and see what the zeros are. Okay, so I went ahead and graphed x squared plus 1. And it actually is located with its vertex at 0, 1. Because there's nothing being added or subtracted from the x, and there's 1 being added to the whole function. So that means it's a horizontal slide of 0 units and a vertical slide of 1 unit up. And so when we think about the zeros, another way to say the zeros or the solutions is the x-intercepts. So if we look at this graph, and we considered the place where the graph crosses the x-axis, there actually are no zeros. At least there are no real zeros, because this never crosses the x-axis. Okay, so let's look at number 2. This one says, find the roots of the following equation. X squared plus 16 equals negative 9. Well, now this is one of those that we could actually use the square root property on, because we can isolate the x squared all by itself, and because there's not an x squared and an x term. And so I'm going to simply solve this by just subtracting 16 from both sides, and I end up with x squared is equal to, let's see, negative 9 minus 16 is negative 25. Now, typically, I might get to this point and think, I'm going to take the square root of both sides, and I might think, uh-oh, I can't do this. I'm trying to take the square root of a negative number. Well, it turns out that you can take the square root of a negative number. It's just that you won't get a real number solution. You'll get an imaginary solution. So we'll actually come back and finish solving this in just a moment as soon as we cover some of the key things about complex numbers and imaginary solutions. Okay, so let's just give you a little background. At some point in the history of mathematics, someone was bothered by this type of question that we're trying to solve right now, where we were trying to get a solution and we were forced to be taking a square root of a negative number, which really doesn't make sense, because you think about what a square root is we're looking for a number that when we multiply it by itself gives us this thing called the radicand, the number under the radical. And there's no way you could multiply a number by itself and get a negative number. Because if your original number was positive, positive times the positive is positive. And if it was negative, then a negative times a negative is positive. And so that bothered someone. And so what they decided to do is find a way of taking the square root of a negative number by defining the square root of negative 1. So let's complete this statement. You can find solutions that are non-real numbers if you define the square root of negative numbers, which is why imaginary numbers were invented. And the imaginary unit that was created was called I. I think maybe for obvious reasons, imaginary starts with I. And it was defined as the square root of -1. So what they said is that the square root of -1 was equal to I, this imaginary unit. So you can use the imaginary unit to write the square root of any negative number. And here's how we could do it. So let's go back up and look at this question. We were trying to take the square root of -25. Well, we can use that product property to split -25 up into two of its factors. So if what we did is wrote one of its factors as -1 and the other one to be 25, so if I rewrote the -25 as 25 times -1, and then I went ahead and split those up and gave them each their own radical, I could write that as the square root of 25. All of a sudden I can do that. And the square root of -1, which they actually defined to be I, then I could go ahead and take the square root of this -25. It would just simply be the square root of the 25, which is plus or minus 5. And then the square root of the -1 is defined to be I. And so we say that the square root of -25 is plus or minus 5i. And that's how we can take the square roots of negative numbers. Let's go ahead and look deeper into this on the next page. So as we said, the imaginary number is the square root of a negative number. And these imaginary numbers can be written in the form b times I, where b is a real number and I is the imaginary unit. Now the square of an imaginary number is the original negative number. So let's do this little simplifying with imaginary numbers. Example A asks me to take the square root of -1. Well, that's in fact the definition of what I is. It is the square root of -1. So the square root of -1 is just simply I. Now what about the square root of -2? Well, I can rewrite this as the square root of 2 times the square root of -1. So I broke off that imaginary unit, and I know that the square root of -1 is actually equal to I. But there's not really anything I can do with the square root of 2 unless I want to approximate it as a decimal. So I could just actually write this as plus or minus the square root of 2i. So again, the square root of -2 is plus or minus the square root of 2i. Or plus or minus I times the square root of 2. What about the square root of 4? Well, this time I can break out a perfect square out of this -4. One of the factors of -4 is 4 itself, and the other is -1. Well, 4 turns out to be a perfect square. The square root of 4 could be plus or minus 2, and then the square root of -1 is, of course, I. And so the square root of -4 is plus or minus 2i. And finally, I squared. Well, let's see what we said. We said I, this part, was the square root of -1. And so if I took the square root of -1, which is what I is, and I squared it, well, squaring and square rooting undo each other. And so the square root of -1 squared is -1. Let's move on and do a few more that are a little more complicated. So they asked me to express the numbers in terms of I, and I am asked to take the opposite of, so the negative out in front means opposite of, the square root of -96. So I've got this negative out in front. Now if I break out the perfect square factor, or I guess we just break out the 96 and then the square root of -1, I know that the square root of -1 is I, and then it's telling me to take the negative square root of 96. So what that means is rather than wanting the principal root, which is usually the positive root, they just want you to give the negative root. And so then I can go ahead and there's a perfect square factor of 96. It's 16. So I could rewrite this as the square root of 16 times the square root of 6. Of course, the square root of -1 is I. And so when I get this all completely simplified, I have the negative out in front. I have the square root of 16, which is 4. And so the minus out in front is saying we're taking the negative root, not the positive root. And then times the square root of 6 and times I. So how we usually write it was we'll write the I next, and we'll write the radical at the end. And that way, by writing the radical at the end, we're not mistakenly thinking other things are under the radical sign. And that's our final answer there. So negative 4I times the square root of 6 is the same as the opposite of the square root of negative 96. Okay, so let's take a look at example B. So I have a 2 that's being multiplied by the square root of negative 36. Well, the negative 36 can be broken down into a 36 and a square root of negative 1. Well, the square root of 36 is, of course, 6, and the square root of negative 1 is I. And so if I go ahead and do my multiplying of the 2 and the 6, I get 12, so it's 12I. And of course, we could also have plus or minus, because when we take the square root of that negative 1, we get plus or minus I. So that is our 2 times the square root of negative 36 is plus or minus 12I. So I want you to try example C as a you try question. So go ahead and pause the video now and express these in lowest terms and in terms of I. Okay, so check out your answer. You should have gotten plus or minus 55I. All right, let's go ahead and try to put this in practice by doing a little solving of some simple quadratic equations that happen to have imaginary solutions. So looking at example A, we're asked to solve x squared is equal to negative 144. So I know right away that means I'm going to go ahead and have to take the square root of both sides to cancel out the squared on the x squared. When I have done this in the past, we would say, oh, we can't do this. We can't take the square root of negative 144. But now we know we can, because we can simply split this up into the square root of 144 times the square root of negative 1. And that gives me plus or minus 12, which is the square root of 144. And then the square root of negative 1 is I. So that means my two solutions are plus or minus 12I. And one last example here. So to solve this, I'm going to go ahead and subtract 90 from both sides. So I'm trying to isolate the squared term. And when I do that, I have a negative 90 on the other side, which then I could divide both sides by 5. And that gives me x squared equals negative 18. So now I'm going to go ahead and take the square root of both sides, which this time I don't have a perfect square. I'm going to have to do a little work on. So I know that I can break this up into the square root of 18 times the square root of negative 1. Well, the square root of 18 can be broken down further into the square root of 9 and the square root of 2. And that way I've gotten out the perfect square factor of 9. And finally, simplifying this, I get x is equal to plus or minus 3, which is where the square root of 9 comes in, I, which is where the square root of negative 1 comes in, then the radical that I could not reduce any further is the square root of 2. So my two solutions would be positive 3I times the square root of 2 and negative 3I times the square root of 2. So there are my two solutions. And let's move on to the next page. Okay, so in the previous few questions, we ended up getting answers that looked like this. There'd be plus or minus, there would be a real number like in this case 5, and an I, the imaginary number, which is the square root of negative 1. And so we actually call this like an imaginary number. But there are also these things called complex numbers. And complex numbers can be written in the form of a plus bi, where a and b are real numbers and I is equal to the square root of negative 1, or an imaginary unit. Now the reason something in the form of a plus bi is called a complex number is it's more complex. It's not just a real number. It's not just an imaginary number. it is a combination of the two. And so it actually has a real part and an imaginary part. The real number part is the A, and then it's what's being added to it is an imaginary part, which the imaginary part has the I. And that's the imaginary unit is I. So if I had something like 6 plus 5i, then the 6 part would be the real part, and the 5i part would be the imaginary part. Okay, so on a side note, this is a little note I want you to pay a little attention to. It says two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So, you know, each of those parts has to be exactly the same to be equal, which makes sense. I mean, for two things to be equal, they would have to be the same. Now, there's something called the complex conjugate of a complex number. And the complex conjugate of a complex number is let's say the complex number was a plus bi, or in the example I'm using here, 6 plus 5i, then its conjugate would be a minus bi, or in our case, it would be 6 minus 5i. So the complex conjugate keeps the real number part exactly the same, but it changes the sign on the imaginary part, because in the original 6 plus 5i, the imaginary part was positive 5, and in its conjugate, the imaginary part is negative 5. So complex conjugates have the same real number part, but they have opposite imaginary parts. Now you notice that most of the time when we solve quadratic equations, we get two solutions. And if a quadratic equation with real coefficients has non-real roots, so if it has non-real roots, those roots are going to be complex conjugates of each other. So if one of your solutions was 6 plus 5i for your quadratic equation, then the other one would have to be 6 minus 5i. So let's test out your understanding of a complex conjugate. In example 4, we're going to find the complex conjugate of, in A, 8 plus 5i. Okay, so the complex conjugate keeps the real number part the same and changes the sign on the imaginary part. So that means this real number part is going to stay the same. It's going to be 8. And the imaginary part, which is 5, is now going to become negative 5. So this becomes a minus 5i, and that's the complex conjugate. So now B is a little bit tricky because B just says 6i, and it actually looks like it doesn't have a real number part, which technically the imaginary part is 6i, and the real number part is 0. So this is really 0 plus 6i. So to get the conjugate, I keep 0 exactly the same, but I change the plus 6i to a minus 6i. So that really means that the conjugate is technically just minus 6i. So you don't have to put the 0 there, but that is your conjugate. Okay, so we've come to our final example, and example 5 asks us to find complex zeros of a quadratic function, and the directions go on to say by using completing the square method. Okay, so let's take a look how we could use completing the square to find the complex zeros of this quadratic function. Well, first of all, when we're solving any quadratic function, we know that it means we're trying to find the zeros, and so we want to find out the value when the function's output is 0. So we're going to go ahead and put 0 in for f of x, and then we want to complete the square. So when we're completing the square, we have to make sure that we have a perfect square trinomial. And x squared plus 10x plus 26 is not a perfect square trinomial. So what we're going to want to do is try to clear the slate of that 26. And we know that if there was a different number there, that would make that a perfect square trinomial. And so we want to just kind of get rid of that 26 and sort of get, so we have a blank slate there, and we can just add whatever constant term we want to make it a perfect square. So I'm going to go ahead and subtract 26 from both sides, and that way I have a clear slate here, and I just can add whatever I want to make this a perfect square. So what I have to do is figure out what do I want to add here to make this a perfect square trinomial. And whatever I add there, though, I'm going to have to also add to the other side, because we have to use that addition property of equality, so if we add it to one side, we have to add it to the other. So I know that the way that I can complete a square is I have to take that middle term, which is the 10, and I have to divide it by 2, and then I have to square it. So it's always the b over 2 squared. And so I know that 10 divided by 2 is 5, and 5 squared is 25. So what I'm going to want to add to make this a perfect square trinomial over here is I want to add 25. So I'm going to add this number. That'll make that a perfect square trinomial, and that means I have to add that same thing on the other side. So I'm keeping it in balance by doing the same thing on one side as I'm doing on the other. Now I know on this left-hand side that 25 minus 26 gives me a -1. Okay. On the right-hand side, I have this perfect square trinomial now that I can break down. I know that it's going to be found by taking the square root of the first and the last terms, and the binomials will be identical. The sign will come from the center. So these are all things that we've been, talking about in depth in prior lessons. So I know that the sign's going to be a plus here. I know that the leading term of binomial is going to be x, and the constant term is going to be a 5. And there's 2 of them, so it's x plus 5 times x plus 5, which is x plus 5 squared. Okay, so now we have just a couple more steps here to solve this. So binomial squared. So I could get rid of that squared, which is how I'm going to get to be able to solve this, by taking the square root of both sides. Well, we just learned that the square root of -1 is I. So on this left-hand side, we just have an I. Actually, we have a plus or minus I, because when you take the square root, there's always 2 possibilities. On the right-hand side, that square root just cancels out the squared, and it leaves me with just x plus 5. And we have one last step to solve this, because what we want to do now is get rid of that 5, and so we're going to subtract 5 from both sides, and that leaves me with my answer for x to be -5 plus or minus I. And the reason why I wrote that -5 first, because that's the real number part, and the imaginary part is the part that has the I, and it actually has a coefficient of 1 in front of it. So it's -5 plus or minus 1I. So that really means there's 2 solutions. The one solution is -5 plus I, and the other one is -5 minus I. And those are my 2 solutions. All right, so we'll go ahead and complete example B together, because this is a little bit tricky, so I won't leave this one as a you try for you. So, okay, we're going to solve g of x is equal to x squared plus 4x plus 12. So that first step is to go ahead and put 0 in for the function, and now we want to sort of clear the slate, because I know that x squared plus 4x plus 12 is not a perfect square trinomial, because that last term would be have to be half of the middle term. It would have to be half of 4 squared. So it actually would have to be 2 squared or 4, and it's not. So I'm going to go ahead and get rid of that 12 by subtracting it, sort of just clear the slate, bring it over to the other side. And then on the other side, I just have x squared plus 4x. And I know now that I want to add something here to make this a perfect square trinomial, and I'm going to make sure I add it to the other side as well. And what I'm going to have to add, I've already found, it is right here. I have to add 4. So that would make it into a perfect square trinomial. So I'm going to go ahead and add that on both sides. Right here and here, I'm adding it to both sides. On the left-hand side, when I add that 4 to the -12, I get -8. And on the right-hand side, I can go ahead and factor this. So I know that it's a perfect square trinomial, so it's going to fit the form of 2 identical binomials. The sign of the term between the terms is going to come from the middle term, so it's going to be a plus. So the square root of x squared is x, the square root of 4 is 2, and there's 2 of them, so it's the x plus 2 quantity squared. Okay, now we're at the point where we can go ahead and take the square root of both sides, because we can cancel out the squared. That leaves me with the square root of -8. So let's take a look at that. We know that we can break that down a little bit. First of all, we know there's a perfect square factor in it, so I'm just going to rewrite this as the square root of 4, which is the perfect square factor that's in there, the square root of 2. So 4 and 2, 4 times 2 is 8, and also negative 1. So 4 times 2 times negative 1 is negative 8, so I've broken that down. And on the other side I have x plus 2. So now the square root of 4 is 2. The square root of negative 1 is I. There's plus or minus. And then we have the square root of 2. So it's plus or minus 2I square root of 2. And that's equal to x plus 2. And my last step would then be to subtract 2 from both sides to get x by itself. And now my solutions are x is equal to negative 2 plus or minus 2I square root of 2. That looks pretty complicated. That's why they're called complex numbers. And that really means there's two solutions there. There's negative 2 plus 2I square root of 2, and there's negative 2 minus 2I square root of 2. Because remember, those are, in fact, written just as a single term. Those are the original complex number and its conjugate, all right, kind of in that same statement. But technically it means that there's two solutions. One is the minus 2, let's see if I rewrite these up here, a minus 2 plus 2I square root of 2, and there's minus 2 minus 2I square root of 2, and those are the two solutions. And so those are our two complex, very complex number solutions. And that does it for today's lesson, so I'll see you in class.